Okay, can you hear me? Is this okay? Is this okay right now, everyone? Okay. So wait a little bit. Các em có nghe tôi nói rõ không các em? Bị rè hả? Tôi biết cái chuyện này. Các em nói mở mic nói lên xem cô có nghe không? Rồi, bây giờ nghe ổn chưa? Có rè nữa không? Vậy bây giờ nghe nó ổn không? Các em có nghe bị rè không? Nó rè nhưng mà nghe hả? Chắc tại cái máy này nó... Để tôi dùng tay phone xem có ổn hơn không? Rồi, ok thôi chịu rồi đó. Nó chỉ có thế thôi, cái máy này nó cũ rồi. Okay, so we almost learned chapter 3. So during these chapters, we have learned some special distributions. For the decreased distributions, we learned about the Bernoulli kairos or Bernoulli distributions. And then we use Bernoulli distributions to define the binomial distributions. Then we define the limiting distributions of the binomial distributions to be the Poisson distributions. Okay, that's about 3 decreased distributions. And then we continue with the continuous one. For continuous, we started with the uniform distributions, and then we continue with the exponential distributions. And finally, last week, we have the knowledge about the normal distributions. Okay, so now to finish chapter 3, we talk about the central limit theorem. This is one of the most important theorem in probability and statistics. Okay, wait. To give you a general idea about the normal distributions. So please look at example 18. Okay, I give you few seconds for reading example 18, and then around 1 minute to think about the solutions for answering example 18. Okay. Okay, so in example 18, it said that we are given SI will be the service term of customer I. And the bank teller shows each customer standing in the queue one by one. It means that after finishing the first one, we continue with the second one, and finish the second one, we continue with the next one. Moreover, we just know the mean and the variance of the service time for expression. Then let Y indicates the total time. Y indicates the total time for 50 customers. Find the probabilities that Y greater than 90 and less than 110. So, how to answer for this question? Okay, first of all, I just summarize the information. We are given that SI will be the service time. SI is the service time. The service. The service time of customer I. Customer I. Okay, and we are given that E of SI equals to 2 and V of SI equals to 1. Okay, now we want to find the probability relating to the random variable Y. Okay, where Y will be the total time. Y is the total time for 50, actually this is the total service time for 50 customers. Okay. Hence, of course, easily, because Y is the total time of the of 50 customers, so easily we can write Y equals to the sum of S1 plus S2 plus Sn, where n equals to 50. Right? Y is written as the sum of n independent random variables, and here n equals to 50. Okay, so we want to answer for the question about probability of Y between 90 to 110. What is this probability? Okay. How to answer for this question? Yes, I already made the recording for these lessons. But it's better if you follow me. Okay. So how to find this probability? This is the probability relating to the random variable y. But do we know the distributions of the random variable y? No. Actually, we don't know the distribution of y. Because here, we just know that y is the total service time for 50 customers. And y is written as the sum of S1, S2, and 2, Sn. But at the beginning, we don't know the divisions. We don't know the division of Si. We just know that Si is the service time for each customer I. And we just know it means the average service time and the variance of the service time for each customer. But generally, we don't know the division of Si. So if we don't know the division of Si, of course we don't know the division of Y. So if we don't know the division of Y, so how could we find the probability of Y between 90 to 100? Actually, never. We never able to find the probability of the random variable Y. In case that we don't know its distributions. Okay? So how to deal with this problem? Of course, it's very clear that in this case, we don't know the division of Y. But we still want to calculate this probability relating to Y. Okay? And in this case, the unit of course will be the approximations. Okay? Because we don't know the distributions of Y. So to calculate the probability relating to Y, of course we need to approximate it. Okay? We need to approximate for this probability. Okay, and the tool allows us to approximate the probability of the random variable Y in case that Y is written as the sum of n independent random variable Si. That is the central limit theorem. Okay, so the central limit theorem will allow us to approximate the distribution of the random variable Y in case that we don't know its distributions. But we know that Y is written in form of the sum of n independent random variable Si. And we know the mean and we know the variance of each of the random variable Si. Okay? We will return to the central limit theorem to see clearly how it can approximate this probability in this case. Okay? The second example. Now the second example. Look at questions 21. This is one of the final exams. Let I copy it to the board. Okay. The second example. Oops. Okay, so I left you a few seconds for reading this exercise. This is the question 21 in the final exam of semester. I don't remember which semester. But anyway, please look at these questions and imagine about the answer that we should give for these questions. Okay? Okay, here we set up the scores of the students. So if we left S will be the scores of students in the exams. Okay, then S follow normal distributions. With the mean is the average score, the mean mu and the variance sigma square. Where in this case we have mu actually see the mean of S. The mean of S equals to 639.2, and the standard deviations, this means sigma equals to sigma square equals to 118.6 square. Okay, the standard definitions. Now, question A, determine the score such that 90% of the candidates taking the exam have a score greater than this score. This is just the questions about the normal distributions, right? It means not looking for S0. Okay, question A, actually we're looking for S0 such that the probability of S, the candidates, 50% of candidates taking the exam have the score greater than this score, so S greater than S0 equals to 0.7. Okay, and you will looking for S0 using the function phi. Okay, we return to do it later. Now I try to focus on question B. A random sample of 200 candidates taking the exams was selected. For the probability that there are between 100 and 120 candidates whose scores are greater than 650. So here we're interested in the number of candidates whose scores greater than 650. So in this case, one event will be a student has the score greater than 650. This is our interesting event. Okay, this is the event. This is our interesting event. Okay, and we consider the number of events or the number of students greater than this score is between 100 to 120 among a sample of 200 candidates. So in this case, if I left Y will be the number of candidates or students, the number of students who get scores greater than or equals to 650. So anyone can tell me what's the distributions of Y's? Everyone, what's the distributions of Y's? What is the distribution of Y in this case? If Y indicates the number of students who get the score greater than 650 among the sample of 200 candidates, so what is the distribution of Y? Anyone else? Do you recognize? What should be the distributions of Y in this case? Y must follow binomial distribution, right? With two parameters n and p, where n equals to 200 and p equals to, what is p here? What is p here? P is, okay, in the binomial distributions. The binomial distribution requires the number of events among the sample of n trials. Okay, so in this case, as I told you, the events will be students who get the score greater than 600 or 50. And then we count the number of students who get the score greater than this score among the sample of 200 candidates. So in this case, we're considering the number of trials, which is 200 candidates. And we count how many students who get the score greater than this one. This means we are considering the number of events, the number of success trials among the sample of 200 trials. Okay, so that's the reason why must be the binomial distribution. It's exactly the definitions of binomial distributions. And in binomial distributions, the parameter P will be the probability of success. What is success? The probability of success is mean the probability to get one event happened. And in this case, the event happened. It means that one student get the score greater than or equals to 650. Okay? So P will be the probability that a student get the score greater than 650. And the score of one student indicated by the random variable S. So P must be S greater than or equals to 650. Okay? And of course, looking for this probability, you're able to do it. Okay? This will be the probability of set with standardized greater than 650 minus mu over sigma. And then using the integral, you should be able to get the value of P. If you already know two parameters N and P in binomial distributions, of course now you can easily find the probability of Y between 100, between this means greater than or equals to 120. Okay, so using the binomial distribution formulas, this should be the sum of C n k, n is 200, k, p power k, q power 200 minus k, where k equals to 100 to 120. So different from the first example, the example 18 on the slides, we don't know the distributions of Y because Y is just the sum of n independent surface term, right? Here, shown off. In this example, Y is written as the total term, and we don't know the distributions of each of the surface term for customer I. So of course we don't know the distribution of Y. So surely, to calculate this probability, we must be we need to use the approximations. But now, in this exercise, the question is 21 here. We know exactly the distribution of Y. So to calculate the probability of Y between 100 to 120, we use the formula of the binomial distributions with C and K. But the problem is that here in this sum, we need to add totally 21 terms into the sum, right? So there's so much terms to calculations to get the precise value for this probability. So of course here we can get exactly the values for this probability using this formula. But it's very inconvenient. We need something more simpler because here, imagine that I want to live here from 100 to 120. If I increase this number, if I increase this interval, so more and more times you need to you need to consider into the sum. Suppose that you need to take the sum up to 100 terms. So how could you do it? How could you use your calculator to take the sum of 100 terms? Do you understand the problem? Do you get the problem? The problem here is that even you know exactly the division of y, but to calculate this property, you need to take the sum for so many terms, and it's very inconvenient in some case. For example, this case, you need to sum up 21 terms. From 100 to 120, we have 21 terms, right? So to overcome this problem, even we can know exactly this property using the binomial divisions. But now we don't want. We want something simpler. So instead of directly calculate this property using this formula, we will approximate it. Okay? We will use the approximation to get the simpler formula. Even it can be slightly different from the true values of this property, but it will be the approximation, a good approximation for this property. Okay? So once more time, we have the motivations to get the tool. We need some tool allow us to approximate for the division relating to y. Here y also written as the sum of n independent random variables. Why? Because y follow binomial divisions. So cos y also written as the sum of n Bernoulli trials, right? From 1 to n. When h of si follow Bernoulli trial with property b. So in the first example, or in this example, both of them, the random variable y can be written as the sum of n independent random variables. And we have motivations to approximate for the property relating to y. Okay, and return to the slides. I will introduce you the tool allow us to approximate, to get the approximations in this case. That is called the central limit theorem. Central limit theorem. Okay. Go to the slide. Okay, this is the central limit theorem. Let's I copy this and summarize in the board because here I can't write on the slides. Oh, no. Okay, so the central limit theorem. Central limit theorem. The central limit theorem said that if we're given n independent random variables, s1, s2, the sequences of random variable s1 to sn. Okay, and they are independent, and they are identically distributed. Identical distribution, identical distributive. Identical distributive, this means that they have the same distributions. Okay, they have the same distributions with the mean are given, the mean of Si equals to mean, and the variance of Si equals to the variance of each of them will be sigma squared. Okay, in this case, if we're interested in the new random variable y is written as the sum of n independent random variable s1 until sn. So we write s1 plus s2 plus sn. Or if we're interested in the average of them, the new random variable s bar. S bar is the average of n independent random variable sn. So s bar will be the sum of s1 plus s2 plus Sn divided by n. Okay, S bar is the sample average of the given n independent random variables. In this case, it said that in case we don't know distributions of Si, or Si can follow any distributions, except the normal distributions. Okay, because if Si already follow normal distributions, so nothing to be approximations, we can directly use the normal distributions. Okay, now the central limit theorem will be very useful, will be applicable in case that the random variable Si can follow any distributions, but not normal distributions. Okay, even we can know distribution of Si, this can follow any distribution. For example, the uniform, the exponential, the binomial, the Bernoulli, the Parsons. Okay, but we don't know, or in case that we don't know distribution of Si. Okay, in both cases, if we interested in the new random variable Y can be written as the sum of n independent Si, or we interested in the sample average S bar. In this case, the central limit theorem said that we can approximate distribution of Y by using the normal distribution. With the mean of Y, the mean of sum equals to the sum of mean, so we have n mu. The variance of sum equals to the sum of variances because of independence. Okay, and we can also approximate the distribution of S bar using normal distributions. In this case, the mean of the average is exactly equals to the mean of Si. The variance of the average equals to sigma squared over n. Okay, you can prove this. You can prove from this. Of course, we see the approximations. So we need n is enough large. Okay, we need n is large. Okay, n must be large. Larger values of n, you can get better approximations. So n is large. Okay. So this is the central limit theorem. Okay, once more time, we will use the central limit theorem. Firstly, if we have the random variable Y can be written as the sum of n independent and identical distributions Si, or we're interested in the average of n independent random variable Si. In this case, either we know or we don't know distribution of Y and distribution of S bar, but we want to approximate it by the normal distributions, then the central limit theorem will be applied in this case. Okay. Okay, so return to example 1. Let's see together how the central limit theorem can answer for the property of the total term between 900 to 150. Okay. So as we already discussed now, in this case, because we don't know distributions of Si, we just know that Si indicates the surface term for customer I, and they are independent with the mean equals to 2 and the variance equals to 1. So in this case, the total term is written as the sum of n independence random variable Si, and we don't know the distribution of Y. Okay, surely we don't know the distribution of Y. Okay, so to use the central limit theorem, the first step we need to write, we need to know the average and the standard, the average and the variance of the random variable Y, right? So I will write the mean E of Y equals to the mean of sum equals to sum of mean. So we have 50 multiply, the mean is 2, so we have 100. V of Y, the variance of sum equals to sum of variances, of course, in case of independence. So in this case, we have 50 multiplied 1 is equals to 50. So the central limit theorem said that in case n is enough large here, n equals to 50. So y will approximately follow normal distribution with the mean. The mean equals to 100 and the variance equals to 50. Okay, this is central limit theorem. Okay, this is the statement from the central limit theorem. Now, find the probability of y between 900 to 110. At the beginning, we don't know how to calculate for this probability because we don't know the division of y. But now we already apply the central limit theorem, and we assume that we approximate the division of y by the normal divisions. So here, directly, we use the normal divisions to calculate this probability. Okay, you should be familiar with the normal divisions. So I will standardize the random variable y. So I have the probability of y minus its mean over its standard deviation v of y. E of y, y minus e of y. It's very difficult for writing. Over square root of v of y. We do the same thing for the left and the right of the given equations. So we have 90 minus e of y over square root of v of y. Here we have 110 minus e of y over square root of v of y. Okay, so because we already approximate the division of y by the normal divisions, hence standardizing normal divisions, we have standard score. Right? This time we approximately follow normal division and 0 and 1. Hence, this probability will be approximated by the probability of z between what? The left is 90 minus the mean. Minus the mean is 100. So we have minus 10 over square root of 50. Square root of 50 will be 5 square root of 2. So the left I have minus square root of 2. The right we have square root of 2. Okay? Where z approximately, z follow normal division with the mean is 0, 1. So this probability easily you can use your calculator. This is the integral from minus square root of 2 to square root of 2. The density function of the standard score we have 1 over square root of 2 pi e power minus z squared over 2 dz. Okay, then you should get the answer. So we have done. We see the question about the about the central limit theorem. Apply for the case of the continuous random variable. Okay, so in this case, y is the continuous random variable because y is the total term. The term, of course, it should be continuous. So you can see it's very convenient. It's very easy to apply the central limit theorem for the case that y is the continuous random variable. Okay, we just use the knowledge about the normal distributions, and we do it as the question for the normal distributions. Nothing new. Okay, as long as that, you should recognize where we should use the central limit theorem. Then apply the central limit theorem. It's just using the normal distributions. Okay, is it clear for you, everyone? Any questions? Is this okay? Any questions? If you have any questions, so just raise your hand or turn on the microphone. Don't worry. So understand clearly? Yes or no? Everyone, are you following me? Yes or no?
How do we know? How do we know?
Sorry? Frank?
How do we know when n is not unique?
So when will we know? When will we know what?
N and number 5 is not enough.
Sorry, I can't hear you. The sound is quite poor. I can't hear. So and because see in the questions it said that we are considering why is the total part of the bank teller spent serving for 50 customers. So the end is 50. Because the total part for 50 customers, so we take the sum of n independent random variables s from s1 to ssn, where n equals to 50. I don't know, is this your questions? Fair? Or maybe you can type your questions on the chat box so I can follow you. When can we know n is large enough? Okay, actually we don't have any answer for these questions because it depends on different situations and can be different for different distributions. If the underlying distribution applied is very similar to the normal distribution, so n don't need to be very large. But in some cases, if the random variable y is very far from the normal distributions, it's so different from normal distributions, so we need n is very large. So actually, we don't have any final answer about how large the sample size. Okay. So in experiment, which usually use n is around 30 or more than 30, but it's not a good answer because it's just approximations. So if you use a larger sample size n, then you have better approximations. If you have n is so small, then you have very poor approximations. That's all. Okay, it's not right or wrong. It's just better or very. It's just better or not about the quality of the approximations, right? So you shouldn't be worried about the number and in the questions. Okay, you just need to pay attention about the signal where when we should use the central limit theorem. Okay, and the answer about when we should use the central limit theorem is depending on whether y can be written in form of the sum of n independent random variable si, or we are interested on the average of them. And we not know the division of Si. All the division of Si we know, but it's not convenient for calculating. So this is the signal to use the central limit theorem. You shouldn't worry about the sample size n. Okay, that's my answer. Is it clear for you? Fine? Okay. Okay, so if no questions, return to examples about the scores of students in the exams of Vietnam National University. What's the difference here? Here, as we have seen that to calculate this property, we also refer to use the central limit theorem to do the approximations. Because here even we know exactly the division of y, which is following the normal divisions. But because we don't want very big, we don't want so many terms adding to the sum. That's the reason why we need to use the central limit theorem. But what is the difference here? What's the difference from the previous example? So anyone if you recognize that in the example about the total time of the customer, the total service time of the customer, y will be the continuous random variable, right? But now here, in this case, y is the decreased random variable. Let's see the key difference between them. In the first example, because y is the total time, so of course y must be continuous. But now y is just the number of students who verify the score at least 750. So y is the number of students. This means that we're counting 1, 2, 3, 4, 5, and so on. So y must be decreased. Y is the decreased random variable. Okay. But we are using the central limit theorem. This means we are using the normal distributions. That is one continuous distribution to approximate for or decrease distributions. Okay. It doesn't matter. In the first case, it doesn't matter that we are using the normal distributions to approximate for or continuous distributions because both of them they are continuous. But now the normal distribution is continuous. The normal distribution is decreased. We're using the continuous distribution to approximate for the decreased distributions. Okay? So, look at the slides. Here, on the slides, I give you two examples. In example 17, this is the illustrations about the central limit theorem applies in case of the sum of n independent uniform distributions between 0 and 1. So you know that the uniform distributions between 0 and 1 is the continuous one. So using the central limit theorem, I will start it with n equals to 1. Okay, here I apply the central limit theorem for the average of S1 until Sn. And here I increase n firstly from 1, then n equals to 2, then n equals to 3. So you can see that in this case, we just use n equal to 3, but the approximations is almost close to the normal distributions. Okay. It seems very similar to the normal distributions. Started for n only equals to 3. And then if we increase n equals to 30, then you can say that it's exactly follow the normal distributions. So, how about the next case? In the next case, I try to apply the central limit theorem in case of n independent Bernoulli trials. So you know that the sum of n Bernoulli trials is will be the binomial distributions, right? Here we apply the central limit theorem in case of decreased distributions, which is the binomial distributions. I also started with n equals to 1, and then n equals to 2, and then n equals to 3. You can see that in case of n equals to 3, in the uniform distributions here, n equal to 3 in case of the uniform distributions, it's almost similar to the normal distribution started from n equal to 3. But now, if we use n equal to 3 in case of a normal distributions, you can see it's totally different to normal distributions. Here, it only has 1, 2, 3, and 4 bars for decreased distributions. Of course, how this can be similar to the normal distributions is so far different. And then we started to increase n up to 30. If n equals to 30, you can see that generally is similar to normal distributions. But it still be decreased. See, this will be the vertical, this will be the separated vertical parts. So if we increase n, will be larger and larger. So of course, the decreased distribution it seems to be continuous, but actually no. the decreased distributions, it still be decreased distributions. It's even you increase and will be larger. So here, in the given two examples, I want to show you two things. First thing is answering for the questions of volume fact. That is about the number of sample size and how much is enough. So you can see in the first case, n equal to 3 already good to do the approximations. But now n equal to 30, but it's still not, it seems to not enough. Okay, so we don't have any fixed value for the sample size for using the central limit theorem. It's up to different case. Okay, sometimes it can be 30 is enough width, sometimes it can be 50, sometimes it can be 100. We don't have any final answer for the sample size. Okay, but here I want to show you that you can see we will have the problem in case that we want to apply the central limit theorem for the decreased distributions. Okay, the problem is that if we use the continuous distribution, which is the normal, to approximate for a decreased distributions, for example, the Poisson's or the binomial distributions, so surely you should get some errors. Okay, some significant error. The significant errors will is derived from the differences between the continuous and the decreased distributions. Okay, so to overcome this problem, go to the last class. Okay, we have a trick. This just the trick. It's not the theory. The trick is mean that it's just the tool to help us to improve the approximations. It's not the it's not the method. It's not the theory. Okay, and generally it will be useful in some cases. It's not only true for every cases, but especially we trick. It's applicable and very useful in case that we have the central limit theorem applied for the binomial distribution and the Poisson distributions. Okay, here, this is the continuity corrections for decreased random variables. Except that in case we are interested in the random variable y, which is the sum of n independent random variables I. So if y is the number of events, this means that we're counting 1, 2, 3, 4, 5 among the sample of n independent samples. For example, the binomial or the Poisson distributions. If the values of n are the integers, okay, the values of n are the integers. In this case, the probability of y between the interval L to U. Before we use the central limit theorem, we will increase or decrease. We will increase or decrease the given interval with the number plus or minus 0.5. Okay? So as I told you that, it's just the trick. So don't ask me why we use the number 0.5 or why don't we use 0.2 or 0.1. No, it's just conventions. Okay, it's just conventions. It means that we choose it for convenience, just for convenience. Okay, we will increase or decrease the given interval with the number 0.5, such that the new interval, new contains the values as in the original interval. After that, we apply the central limit theorem as usual. Okay, return to the box. This will be better for explanations. Okay, so for example, that we want to find the probability of y between age to 10. Okay, and here y is supposed to follow the normal distribution with the mean with n and p. Okay. So because y is following the normal distributions, to apply the approximations using the central limit theorem. The continuity correction setup, we must increase or decrease the given interval with the values 0, 5, such that the new interval must contain the same values of y as in the original one. Okay, so what does it mean? Because y is just counting, so from age to 10, we have how many values? We have number 9. So we have age 9 and 10. Okay, if y between age and 10, so we have 3 values, age, 9, 10. So we will, if we decrease 0, 5 to the left and increase 0, 5 to the right. Now we consider the probability of y between 7 for 5 to 10 for 5. So you can see that if y greater than or equals to 7 for 5 and less than or equals to 10 for 5, then the values of y can be received to be age, 9, and 10. It's still the same, right? Because y are just the integral values. So between 7 for 5 to 10 for 5, the values of y still be age, 9, and 10. It will be the same. It will be the same as the original integral or the original interval. It means that this probability and this probability actually the same. But if we apply the central limit theorem, which is the continuous one, so the interval with 0 for 5 increasing or decreasing, it will be closer to the continuous case. So that's the reason why we apply the central limit theorem. After using continuity corrections, this will be better if we use for the original one. Okay? Now, using this probability for the central limit theorem, don't use the central limit theorem for the first interval. Okay? And pay attention that, as I told you, we must increase or decrease with the number 0, 5, such that the new interval must contain the same values as on the original one. It means that not only true, or it's not always true to reduce 0, 5 from the left and not always increase 0, 5 from the right. No, it's not true. It depends on different situations. For example, if we need the probability of y greater than age and less than or equals than 10. So in this case, the interval from age to 10 is here. Greater than age, so we only have 9 and 10. We only have 2 values, 9 and 10. Okay. In this case, should we decrease age to 7 for 5 and increase 10 to 10 for 5? No. If you still have minus 0, 5 from the left and plus 0, 5 from the right, as in the first one. Hence, here we have the interval from 7 for 5 to 10. It still contains 3 values, age, 9, and 10. But from the beginning, the original one, we only have 9 and 10. Okay, so now. So in this case, what should we do? Instead of decrease 7 for 5, we will increase 7 for 5, right? So we will write this probability must equal to probability of y. Increasing 0, 5 from the left, we will write 8 for 5 to 10 for 5. Okay? You can see that the interval 8 for 5 to 10 for 5 is still only gets 3 values, 9 and 10. So it's the same as the original one. Okay? So using the central limit theorem from here. Okay, other one. We always do the continuity corrections in case that we want to apply the central limit theorem for the binomial distributions on the Poisson distributions. Okay, because the binomial distribution on the Poisson distributions, get the values are the integral values. Okay, in case that y is written at the form of the sum of n independent binomial distribution. Sorry, in case that y is written as the sum of n independent random variables Si, and the values of y are the integral values, for example, the binomial on the Poissons. Then before applying the central limit theorem, we need to do the continuity corrections. The continuity corrections, it means that you can take plus or minus 0.5 into the interval, the left and the right of the interval, such that the new interval after increasing or decreasing 0.5 is still get the same values of y as on the original interval. Okay, this is clear. Got it, everyone? Here, in the questions about the strong, where is here? Okay, in the question about the strong, we already know that we should use the central limit theorem. I will clean was. We use the central limit theorem to approximate for the property that y between 100 and 120. So, the first step, we need to find the mean and the variance. Okay, to use the central limit theorem, of course, we need to know the mean. We have E. We have E of y. The mean of y equals to n multiplied p. Okay, here n equals to 200, and p is calculated by using the normal distributions. Okay, and the variance, we have v of y equals to n p cubed. Okay, so if we already have e of y and v of y, so we approximate the distribution of y using the normal distributions. But remember that we need to do the continuity corrections. We write y between 130, 945, and less than 120 for 5. Okay, you can see here in this case, I decided to increase 0.5 from the right and decrease 0.5 from the left. Okay, then the interval wants to be the same. Then using the central limit theorem, in this case, we standardize y. We have the property of y minus the mean of y over square root of v of y less than 1 to 0.5 minus e of y. We already found from the previous step, square root of e of y greater than 995 minus e of y over square root of v of y. Okay, then this property we use the standard score is approximated by the property of here on the left, you calculate it by yourself. Okay, this term less than or equals to z, less than or equals to the right term. Okay, then using the integral of the standard score of 1 over square root of 2 pi the power minus s squared over 2 is f. Then you should get the answer. Is this okay? Can you finish this question by yourself? Everyone, is it clear? Any questions? Okay, you have responsibility to finish this exercise by yourself. I already get you the way to do it. Then you finish it by yourself. It's also the good time for your reviewing the knowledge before the midterm exams. Okay, that is all about the central limit theorem, and it's also finished chapter 3. Okay, in the next few minutes, I will correct the questions. Last time we have started in the class. This is about the normal distributions. Not this one. Okay, so in class, we were doing about question 17 to 20. It's right of one, and we haven't yet corrected. Okay, now let I copy. Okay, firstly, we will do together 17. Remember that the normal distributions is one of the most important distributions. So surely, even in the midterm or in the final exams, you still have at least one questions about this. So I want not only you must able to answer 4 questions about the normal distributions. Okay. Okay, 1 minute for you to recover about the knowledge in the class. Then we will solve for each questions from 17 to 20 together. Okay, 1 minute for you. Okay, sorry, that I just lost my connections. Okay, so in these questions, we already given S is the time in the minutes, the time in the unit of minutes. F usually use smartphone. Okay, and it's written down as follow. Normal divisions with the mean, mu, and the variance is not square. Here, the mean equals to 116, and the variance is not square equals to 6 square. Okay, because we're given the standard deviations. So the variance, we must be square root. Okay. For the property that we use this smartphone less than 125.8 minutes per day. So we have question 17 means the property of S less than 1 to 5.8 minutes. That's all. Okay, here S is the time per day. So we have this property is the property of self with standardized S. Less than or equals to be the same because it's C continuous. Okay, less than 1 to 5.8 minus the mean is 116 over standard deviation is over 6. Okay, then use your calculator. I don't know. The value was this one. Use your calculator. We have this property. It's the property from minus infinity to 0. So as we have learned in class, we have 0.5 plus integral from 0 to this form. This time you calculate it by yourself of 1 over square root of 2 pi e power minus z square over 2 bz. And then you should get the answer. Okay, question A is very easy. It's just the knowledge about using normal distributions. Is this okay, everyone? Have you done question 17 by yourself? 18. 18 determines the interval. This is 18. Determine the interval center at 100. At 16, this is the parameter mu in the mean. Such that test the values within this interval is 83 percentage days. So determine the interval such that is center at mu. Center at mu is mean for mu, this is mu, which is 116. Center at mu is mean for mu, we increase the interval time T0, so mu plus T0. And for mu, we also decrease the same interval, okay, the same increments, which is T0. So we have mu minus T0, right? So it means that we want to looking for the interval. The interval we want to looking for is the interval mu minus T0 and mu plus T0, okay? Where mu equals to 116. So the target is looking for T0. If we know T0, so we take mu plus or minus T0, of course we should get the given interval, right? Because center is center at mu. Center at mu, it means we take mu plus or minus the same increments T0, then we should get the given interval, okay? So to answer for 16, we write the probability as belong to this interval, which means as greater than mu minus T0 less than mu plus T0 with the probability is 0.83. Okay. Once more time, working with the normal divisions, we need to standardize. So we write the probability of S minus S mean, which is mu, over standard deviation, which is sigma, less than or equals. The left, you also write mu minus T0, and then minus mu over sigma. The right will be mu plus T0 minus mu over sigma. Okay? Hence, this probability equals to 0.83. Equivalently, we got the probability of mu minus mu will be 0. We have minus T0 over sigma. Less than set, because we standardize as we have said, less than T0 over sigma. Okay? Of the recording already stopped. I need to restart. Okay, so now we have this probability equals to 0.83. The target is looking for T0. Of course, we accept follow normal distribution 0 and 1. So here this probability I will write this is phi of T0 over sigma minus phi of minus T0 over sigma equals to 0.83. Then do you remember about the property of the function phi? Phi of minus s equals to 1 minus phi of s. Right? Hence, here we will have phi of T0 over sigma minus 1 minus phi of T0 over sigma. Okay, here because we have minus T0 here. So, okay, equals to that's 0.3. Equivalently, we have two phi of T0 over sigma minus 1 equals to 0.83. Okay, hence we should get phi of T0 over sigma equals to 1 83 over 2. Okay, then look up from the table of the standard score this value. Look up from table of standard score. Then you should get the values of Z0. Z0 equals to Z0 over sigma, where sigma is the standard deviation we already given from the beginning, which is number 6, right? Hence, we should get D0. You get D0. You get D0, and we should get the interval, okay? Mu plus or minus D0. Then you should get this answer. Read everyone. Is this clear? Is this clear, everyone? Yes or no? Are you following me? Be able to answer for this question by yourself. Okay, this is the question about looking for Z0 from the function phi. From phi, Z0 equals to something. But started from the beginning, you need to model the questions. If you derive to the equation 2 of phi T0 over sigma minus 1 equals to 0.83, I believe that you're able to looking for T0 over sigma. Hence, you should get T0. With T0, then you should get the interval, mu plus or minus T0. Okay? Okay, 19. We don't have much time. 19 and 20. Compute the probability that there are at least 3 days of a week, it means that 3 days among 7 days, in which you will use his smartphone more than 125.8 minutes per day. So here, if I write y will be the number of days among 7 days, such that you will use smartphone more than 125.8 per day. Then anyone can answer me, what is the division of y? Here, if we count the number of days among 7 days, such that we will use smartphone with the 125.8 minutes per day. So what is the division of y? What is the division of y?
Binomial.
Yes, binomial. How about the other student you recognize? So if we count the number of events among a sample of n independent trials, so it should be binomial distributions. We use this many times. Okay, here the events will be a day such that we will use this smartphone greater than 125.8 minutes. Okay, so y follow binomial distribution with n and p. Here n equals to 7 days. And P will be the probability of success. The probability of success is mean the probability of getting one event. So getting one event will be the probability that you will use smartphone more than 125.8 minutes. Moreover, at beginning, we modeled the time we will use smartphone for 1 day will be the random request. And here question 17, we already know the probability that we will use his smartphone less than 128 minutes 1 day. Already calculated here. So now we want P will be the probability that we will use his smartphone greater than this one. So it means that P in question 18 is just 1 minus the probability we found in question 17, right? Okay, so actually this is S greater than or equals to 1, which at 15.8. Okay, this is 1 minus the value in 17. Okay, I write 17. Okay, you replace the answer in 17, then you have P. Then we want the probability of Y at least 3 is mean greater than or equal to 3. Now it's just 1 minus the probability of Y equals to 0 minus Y equals to 1 and minus Y equal to 2. Okay, using the formula of CNK, then you should get it because we're using the binomial distributions. Is it okay, everyone? This question gives you the relationship between the knowledge of the normal distributions and then it returns to the binomial distributions. So as you can see that sometimes in one questions you need to use different distributions. You need to recognize which one we should use. Okay. How about 19? 20. Course. I just need question. Okay. So find the probability of on average of what? Average of weeks. This means that the average of 7 days. We will use this mark for less than this number per day. Find the probability that on average, we will use this mark for less than this number. Now also probability was not the probability relating to 1 day, no. It said that the probability was relating to the average of 7 days. The average of 7 days, okay? So it means that sometimes, maybe in the first day, we will use 100 minutes. The second day, he used 120 minutes. The next day, he used 130 minutes. And now, we're interested on the average of the given 7 days. The probability of this average greater than 125.8 minutes. Okay, so what is our interesting random variable here? We are interested on the average, so I indicate it by H bar. H bar equals to the average of what? The average of 7 days. So H1 plus H2 plus H7 over 7. Right? Maybe I write generally over n. Sn over n, where n equals to 7. Right? We're interested on the average time of the given 7 days. Okay? So what is the distribution of S bar? Do we know the distribution of S bar? Yes, we can know. Because we know that H of Si, the term he used smartphone per 1 day, per day, follow normal distribution with the mean already given. And the variance is much better, okay? Where the mean on the questions is 116, and sigma square equals to 6 square. This is written from the beginning. So each of them Si still follow the same normal distributions. So each of Si follow normal distributions. Of course, S bar also follow normal distributions. Okay. Where the mean, you can remember always, the mean of S bar equals to the mean of Si, which is mu. The variance of S bar equals to the variance of Si, which is sigma square, divided by the sample size n. Okay. So here we have S bar also follow normal distribution, with the mean now equals to still be 106, and V of S bar is mean sigma square of S bar equals to 6 square over n will be over 7. Okay. So if we know that S bar already follow normal distributions, so first you can find the probability relating to S bar. We have probability of S bar. Use smartphone less than 125.8. Okay. So we standardize S bar. We have probability of S bar minus its mean is 116. Over its standard deviation will be 6 over square root of 7, less than 125.8 minus 116 over 6 over square root of 7. Okay. Then using the standard score, we have this is the probability of set less than plus. Write your calculator. Okay, hence this probability of process follow numbers 401. This is 0.5 plus interval from 0 to this value of 1 over square root of 2 pi e power minus s square over 2 dz. Okay, then we should get the answer. The key is that we should recognize we want to calculate S bar. And we should recognize distribution of S bar. If Si follow normal distribution, hence S bar also follow normal distributions. The mean of S bar always equals to the mean of Si. The variance of S bar always equals to the variance of Si over the sample size n. Okay, that is this question. Any questions, everyone? It's clear for you. You should try to redo this exercise by yourself. Okay? Because this exercise is very good for practicing about the normal distributions. It includes almost the knowledge relating to the normal distributions. Is this okay, everyone? Any questions? No questions. So clear or not? Do you understand? Okay, so if no more questions, here all of the examples I take from the midterm and the final exam of the various semester. So you can find it. You can find this file in the video course page on the LMS system. Okay, and try to redo all exercise by yourself. It's really good for practicing. And maybe just within tomorrow, I will upload the quiz for chapter 3, and you can continue to practice some more exercise via the quiz of chapter 3. Okay. Anything else? Any questions about the midterm exams or about the lessons? Okay, so remember that we're going to have the midterm exams on this weekend. We're prepared, and if you have no more questions, so look for your midterm exams. This is up in book. You can use any printed any paper documents. Okay, it means that you can take any paper documents that you want. And don't forget the table of the standard score. Okay, because this is up in book, so the document is up to you. So but don't forget the most important one, which is the table of the standard score. Okay. The midterm results is given within 50 minutes, and the number of questions is usually 20 questions. 20 questions within 50 minutes. So it means that you need to practice very, very frequently for the exercise. You need to almost remember all of the formulas. It's no time for look up from the book. Even this is the upper book is not much based on my experience. It's really short time for reading the book during the exams. If you want to get the high score, you need to practice more and more, and you should be fluent with any kind of the questions. Is it okay? Anything else? Questions? Okay, so if no more questions, so try to review your knowledge by yourself. Okay, and once more time, well prepared, and good luck for your midterm exams. Okay, see you next week. Okay, goodbye everyone, and see you next week.